And the second fact between Lebesgue measure and Lebesgue measurable sets and the Borel measurable sets is the following. Every Lebesgue measurable set E can be represented as a union of two sets, one a Borel set A and a null set N, and the Lebesgue measure of E is same as the Lebesgue measure of the set A. N is a set of measure 0. So, that is the second fact one has. So, let us take, so let A be a Lebesgue measurable, let us take Lebesgue measurable set in R 2, then the set A can be written as E union N, where E is a Borel set in R 2 and the Lebesgue measure. So, lambda R 2 of A is same as lambda R 2 of E. Now, if we look at T of A, so if we look at the set T of A, then that will be equal to T of E union T of N, if T is say non singular. And now, this is a Borel set and this is again a null set. So, Lebesgue outer measure of T of A is equal to Lebesgue outer measure of T of E, which is equal to determinant of, because this is a Borel set. So, determinant of T times Lebesgue outer measure, Lebesgue measure of the set E, and which is same as the Lebesgue measure of the set A. So, this is same as Lebesgue measure of T times Lebesgue measure of A. So, we have used the fact that if A is a Lebesgue measurable set, then A can be written as E union N, where E is a Borel set and N is a null set. That means, the Lebesgue measure of R 2 of the set A is same as the Borel Lebesgue measure of the Borel component of it, that is R 2 of E. So, now if I apply transformation T to it and say T is non singular, then T of A will be equal to T of E union T of N, and just now we observed that T of N is a null set and T of E is a Borel set. So, Lebesgue measure of T of A will be nothing but the Lebesgue measure of T of E, which by the earlier case is determinant of T times Lebesgue measure of E, and Lebesgue measure of E is same as the Lebesgue measure of A. So, that proves that for a Lebesgue measurable set, the Lebesgue measure of the transformed set T of A is same as determinant of T times the Lebesgue measure of the set A itself. So, that proves the theorem completely, namely, that if E is any Lebesgue measurable set, then T of E is also Lebesgue measurable, and the Lebesgue measure of T of E is equal to the determinant of T times the Lebesgue measure of E. So, this is how the Lebesgue measure of a set E in the plane changes with respect to linear transformations. We will give some applications of this now, because there are many nice linear transformations in the plane. So, let us look at the first application of this, namely, so let us take two vectors A and B, A 1 B 1 and A 2 B 2 in R 2, and look at the set which are all set P of all vectors in the plane of the type where the first component is alpha 1 A 1 plus alpha 2 A 2, and the second component is alpha 1 A 1 plus alpha 2 B 2, where alpha 1 and alpha 2 are numbers between 0 and 1. This is called the parallelogram determined by the vectors A 1 B 1 and A 2 B 2. In the picture, it is the following. So, if we have the plane, let us take two vectors, one vector is this vector and other vector is this. So, this is the vector which is A 1 B 1 and this is the vector which is A 2 B 2. Then they determine a parallelogram, the geometric object. So, let us see what is that parallelogram. So, that is nothing but this parallelogram. Okay. So, that is the parallelogram P determined by these two vectors a 1 b 1 and a 2 b 2, and any vector in between. So, this vector, so this parallelogram P is characterized by that this any vector inside here, say call it as x y. So, P is then x looks like alpha 1 a 1 plus alpha 2 a 2, and the second looks like alpha 1 b 1 plus alpha 2 b 2, where this alpha and alpha 2 have the property they are numbers between 0 and 1. So, alpha 1 alpha 2 between 0 and 1. So, this is the point with components alpha alpha 1 and alpha 2. So, if I take okay. So, this is what the parallelogram. So, one can check geometric fact that if I take two vectors a 1 and b 1 and look at the geometric picture of this parallelogram, then if I take any alpha 1 alpha 2 between 0 and 1 and look at this, then this is nothing but the parallelogram given by these two vectors. The claim we want to is that we want to show that the Lebesgue measure of this parallelogram is same as the absolute value of a 1 b 1 a 1 b 2 minus a 2 b 1. So, these are the components a 1 b 1 and a 2 b 2 are the components of the vectors which we started with. So, the claim is that Lebesgue measure of P is equal to the absolute value of a 1 b 2 minus a 2 b 1. Okay. So, to prove this, we are going to show that this P is equal to T of a set E, where T is a linear transformation, T linear, and E is a nice set. And it is not difficult to guess what is T and what is E. So, let us just look at that. So, the claim. So, let us observe that if T is the matrix with the components a 1 a 2 b 1 b 2. So, rows are the vectors which are given, vectors are a 1 b 1 and a 2 b 2. So, the first column is the vector a 1 b 1, second column is the vector components of the vector a 2 b 2. If I look at this transformation T and look at the set E with components alpha 1 alpha 2 in where alpha 1 alpha 2 are real line and they are between 0 and 1. So, what is this set E? This set E is nothing but a rectangle, actually a square in the plane with sides 0 1 to 0 1. And if I look at T of E, so any set alpha 1 alpha 2. So, what will be this? So, what we are saying is the following, that if I look at the set E, so here is the set E, which looks like, so this is the set E 0 0, this is 1 0 1 1 and 0 1. So, if I look at this set and look at the transformation given by T, where T is equal to a 1 b 1 a 1 b 1 and a 2 b 2. If I look at this, then the image of this under this is precisely that parallelogram P, where this is a 1 and a 2 and this is a 1 b 1 and this is a 2 b 2. So, this transforms to this parallelogram. So, if T is this and E is this set, then T of E is equal to P. That is because what is, so let us look at a 1 a 2 b 1 b 2 and a vector is alpha 1 alpha 2. So, what is that? So, that is a 1 alpha 1 plus a 2 alpha 2, and that is gives you b 1 alpha 1 plus b 2 alpha 2. So, that says the vector here alpha 1 alpha 2 goes to the vector there given by this, and that is precisely the parallelogram. So, under the, and this is a linear transformation. So, under the linear transformation T given by this matrix, the unit square changes to the parallelogram, and once that is true. So, this will imply that the Lebesgue measure. So, this will imply the Lebesgue measure of P is same as the Lebesgue measure of in the plane of T of E, and that is equal to determinant of T absolute value times Lebesgue measure of E. But Lebesgue measure of E, that is the area, that is a rectangle. So, it is the area that is equal to 1, and determinant of T is a 1 b 2 minus a 2 b 1. So, that gives us the result. So, that gives us the result that the Lebesgue measure of P is same as the Lebesgue measure of the transformed set T of E, which is equal to determinant of T times the Lebesgue measure of E, and that Lebesgue measure of E being equal to 1. So, that gives us determinant of T, which is nothing but a 1 b 2 minus a 2 b 1. So, this gives us that Lebesgue measure of the parallelogram is the determinant of the given by the vector. So, that is a 1 b 2 minus a 2 b 1. So, this is one of the results that one proves normally in geometry and linear algebra, that the determinant is nothing but a measure of the parallelogram, area of the parallelogram determined by the vectors. Let us look at another application of this formula, how the linear transformation changes. So, let us look at the Lebesgue measure of the unit circle, area region enclosed by the unit circle. So, Lebesgue measure of all vectors x comma y in R 2 such that x square plus y square is less than 1. So, let us look at that. So, let us call the Lebesgue measure of this to be equal to a number pi. We are not assuming anything about pi. We are just saying that the Lebesgue measure of this unit circle is a finite quantity. So, let us see why it is finite. So, here is the unit, right. It is a bounded. So, this is x square plus y square less than 1. So, that is that set. So, this is a bounded set. So, for example, this is enclosed inside this rectangle, inside this square of this is 1 and this is 1. So, this is 0 and this is 1 and this is 1. So, it is enclosed inside this square of length. So, that means that the area. So, this is less than or equal to that, it is a subset of the square, okay. And square is a bounded thing. So, that means the Lebesgue measure of the points say that x square plus y square is less than 1 will be less than or equal to the Lebesgue measure in the plane of the square, which is finite quantity. So, that means that the Lebesgue measure of the region enclosed by the unit circle is a finite number, and this finite number we are just calling it by the number by we are denoting it by the symbol pi. So, pi is the Lebesgue measure of the region enclosed by the unit circle. So, then the claim is that if we look at the annulus region, that is x square plus y square bigger than a square and less than b square, then its Lebesgue measure is pi of b square minus a square. So, what we want to prove is that if I look at here is the bigger circle and here is the smaller one, and this radius is a and this radius is b. So, we are saying the Lebesgue measure of this portion okay, is nothing but pi b square minus a square. That is what we should be expecting from our ordinary geometry that we have been learning in schools, namely the area of the circle is equal to pi r square. So, we will first prove that the area of a circle of radius r is equal to pi r square, and from there we will deduce this fact. So, let us observe that. So, the first thing is, let us take the linear transformation T, which is diagonal, which is given by a 0 0 a. So, we are looking at the diagonal transformation a 0 0 a, and look at the unit circle, area enclosed by the unit circle. So, that is E. So, E is the set of all x vectors x comma y in R 2, such that x square plus y square is less than 1. Then, if we look at any point here and transform it according to this T, that will look like. So, let us look at what will that look like. So, let us look at the transformation a 0 0 a, and let us look at a vector x y. So, that gives us the vector a x a y. So, if this vector had the property that x square plus y square is less than 1, then the transformed vector a x a y has the property that a x square plus a y square is equal to a square times x square plus y square. So, which is less than a square. So, that shows that the unit circle. So, if E is the unit circle, that is x y x square plus y square less than 1, then T of E is the circle, the region enclosed by the circle x square plus y square less than a square. So, that is what we know. So, that means, now we apply our theorem of linear transformations. So, look at the Lebesgue measure R 2 of the transformed set E. So, that is equal to, by the property of the theorem, it is determinant of T times Lebesgue measure of the set E. But determinant of T is equal to it is a diagonal transformation. So, that is a square, and Lebesgue measure of E, which is a unit circle, is pi. So, Lebesgue measure of the transformed set is equal to pi a square. So, that means, the Lebesgue measure of all the points x y such that x square plus y square is less than a square is nothing but pi a square. So, that is the magnification that we are getting. Okay. And so, as a consequence of this, let us deduce for the annulus region, the area is the required Lebesgue measure is pi of b square minus a square. So, for that we have to just observe that if I look at the circle. So, the set of points x y such that x square plus y square is less than b square is a set which is a bounded set, and Lebesgue R 2 of that is finite. So, it is a set of finite outer measure, finite Lebesgue measure. So, I can write that the Lebesgue outer measure of x square plus y square bigger than a square and less than b square is nothing but the Lebesgue measure of the set x square plus y square less than b square set minus the inner circle. So, that is x square plus y square less than a square. And now, everything being finite, I can write this as the Lebesgue measure of the region enclosed by the outer circle. So, that is x square plus y square less than b square minus the Lebesgue measure of x square plus y square of Lebesgue measure of x square plus y square less than a square. So, this is possible because everything is a finite quantity. So, the measure of the difference a minus b, measure of a minus b is measure of a minus measure of b whenever B is a subset of A and everything is finite. So, that property gives you this, and this is pi of B square. Just now we saw pi of A square. So, that is pi of B square minus A square. So, that proves. So, what we are saying is this simple properties help us to confirm that the Lebesgue measure on the plane that we have defined is essentially the extending the notion of area in the plane to a bigger class of subsets, and the usual formulas for the areas that we have been using a priori without any justifications are now being justified by the Lebesgue measure. I will just point out one more extension of this result, namely that the area Lebesgue measure of an annulus region is pi of B square minus A square to something in integration, which is looks like the change of variable formula in multiple integrals. Namely, if you have a double integral then and you change to Cartesian to polar coordinates, then the dx dy, normally we have that formula that when you change dx dy, it should be r dr theta d theta. So, a more rigorous way of saying that for a particular class of functions I want to state and give an outline of the proof. We will not be proving it fully, we will give an outline of the proof. So, let us go to the next application of. So, this is what I just now said, that the Lebesgue measure of the annulus region is Lebesgue measure of the outer circle minus the Lebesgue measure of the inner circle, that is pi B square minus A square. So, this is another application or extension of this result just now we proved. It is called the integration of the radial functions. So, let us look at the theorem says, let us look at a function defined from 0 infinity on the positive on the non-negative part of the real line, taking values in non-negative values. So, that is 0 to infinity. So, it is a non-negative measurable function defined on the non-negative part of the real line. Then the claim is that if I look at the double integral over R 2 of f absolute value of x, x is a vector. So, absolute value means the norm. So, the magnitude of the vector x. So, look at this. So, this is like a composite function. The vector x goes to the magnitude, that is a non-negative real number, and f evaluated at that. So, the double integral with respect to R 2 is given by 2 pi times f r dr d theta. So, that is the claim that this integral is equal to this integral. So, and what is the meaning of a non-negative radial function? F is a non-negative, I should have said here it is a radial function. That means, it depends only on the absolute value of the function. It does not. So, f is a non-negative. So, this is a radial function. So, this you can think it as f composite the magnitude is the radial function, is a radial function. The value of this composite function depends only upon the magnitude of the vector and not on the position of the vector. So, to prove such a result, the proof is a typical application of simple function technique. So, one tries to prove that for simple measurable functions this is true, and then apply monotone convergence theorem and so on. So, I will just outline the steps for a detailed proof. You may consult the textbook. So, let us look at the first step. Let us look at the first step when this function f is the indicator function of a interval a b. When f is the indicator function of a interval a b, where a b is an interval in the non-negative part of the real line. So, a less than b bigger than 0. So, when f is the indicator function, let us compute these both sides and what do they look like. Okay. So, when we So, when f is the indicator function of the a b, so here is the indicator function. So, this is 0 to infinity. So, 0 to infinity means this will give you indicator function will give you only a to b. So, this will be a to b of the function f r. The function is indicator function, this value is 1. So, x r dr. So, when you integrate RdR, you get R square by 2 between A and B. So, when you put the values, you get B square minus A square by 2. So, that is equal to pi of B square minus A square. So, this side is nothing but pi of B square minus A square. And what is this f? So, the indicator function of A B evaluated at the absolute value means you are integrating in the annulus region between the limits A and B. So, it is pi B square minus pi A square. So, in that then it is just equal to pi of B square minus A square. So, this both sides are nothing but the result that we did discuss just now, that the area of the annulus region is equal to pi B square minus A square. So, step 1 is for indicator function, it is that result. The next thing is you look at sets which are either sequences ENs, which are sequences of sets which are Lebesgue measurable, of course, either are pairwise disjoint or a increasing sequence, and supposing for the indicator function of each set En this result holds, then the claim is it also holds for the union of Ens. Okay. So, if for each En the result holds, then the result for each indicator function of each En it holds, then it also holds for the indicator function of the set E. And that essentially is an application of the monotone convergence theorem to the earlier result. So, and then the step 3 is from such things one comes to open sets by the fact that each open set is a countable disjoint union of intervals. So, for intervals that property holds. So, this will hold for every open set, and from the open sets and null sets. So, one shows the corresponding property also holds for null sets. So, open sets and null sets, one goes to the indicator function of any Lebesgue measurable set, because any Lebesgue measurable set can be written in terms of open sets and null sets. So, and then from this one applies the usual monotone convergence theorem technique from the indicator function to non-negative measurable function. So, these are the steps one follows to prove the theorem of this kind. I just want to conclude today's lecture by saying what we have done it for product spaces of two product spaces can also be extended to any finite number of product spaces. So, namely, if you are given a finite number of measure spaces x I, a I, mu I, we define the product of two of them can be extended by sort of doing one at a time iteratively. You can define the product of the space, this x space is x i's 1 to n. You can define the product sigma algebra a I is 1 to n, and you can also define the product measure inductively. One can do that, and so this is called the product space. I will not go into the details of it, but this is useful, and one can also show that if you take product of say some finite number m number and take product of some n number of copies, and then take the product again, that is same as the product of them put together. So, it is same as the product of x i's from n 1 to m plus n. So, these are same. So, one can same with usual identity. So, basically it is saying that what we have done it for two product of two measure spaces can be done it for a finite number of them. So, as a consequence one can define the notion of Lebesgue measurable subsets in R n and the notion of Lebesgue measure in R n. So, this can be done. So, this again those who are interested should refer the textbook for more details. So, what we have done today is we have completed the study of product measure spaces, and with that we have essentially completed what is called the basic concepts in measure theory, namely we have done the extension of measure, then integration of measure, then measure and integration on product spaces. This is the core of the subject, and from now onwards I will be looking at some special topics in our subject of measure theory. Thank you.